Good evening. Today I'm going to be going over my Caesar cipher. Um, this is my final project for spring semester of 2023 for Software Engineering 2. Professor was Professor Mark Reha. So first I'm going to, oh, that went too far. So as a project overview, it's very similar to last semester. So we're running it on the Intel DE10 standard board. This time it contains two FPGA circuits instead of one. This time it has a BCD decoder as well as the cipher circuit. Basically what it is, it's a message encoding algorithm where the user is able to set a key and enter a message, and that key will be used to encode that message, and then to get that message back, you have to enter the same exact key and enter the encoded message. And then if you set it to decode and then enter the message, then you should get your original message back out. The main application is written in C, and we use slide switch as the inputs for the key. And then this is our, like I said, this is our second embedded systems project. Really cool stuff. So for the system design, basically what we have is we have the FPGA right here, which is going to be running the Caesar cipher algorithm. Then we have the C program over here. Those are the main two components. And then we have our peripherals. So we have the GPIO pins, which there's going to be communication from the GPIO pins to the Caesar cipher circuit, and then also back to the GPIO pins so the C program can read it. We're passing 8 bits from the GPIO to the Caesar cipher, and then we're passing it back. And then for this side, we have, sorry, I was getting a little too technical. We have the switches over here. These are the 4 switches that are going to be used to set the key. Those will go to the Caesar cipher circuit as well as to the BCD decoder that will be displayed on 2 7-segment displays. And we have H5 and H9, which one of them is an enabling, so you can enable the whole circuit. That has to be on for it to work. And we also have H5 as well, which is just where you're deciding whether you want to encode or decode. Then we have the application design. Basically all this is doing is like a bridge between the user and the hardware. The user sets the keys and whether to encode or decode, so the majority of it is handled on the actual board peripherals rather than in the program, which is what I wanted. All you have to do is enter a message and it comes out, and you receive your output message. It's more of a black box design, so the user doesn't see anything that's going on in the background or on the FPGA. All they do is enter a message and they get an output message, and they can set the key. So that's pretty much how I wanted to keep it. It's very simple. You just initialize the hardware, you greet the user and tell them the steps on how to operate it. You prompt the user to enter a passphrase, and then next you take the next character string after the message. So after they set the key, they enter their passphrase or their message, and then you take the first character of the string, and then you check to see if it's a space. If it is a space, then we just leave it as a space. Otherwise, we map the character to its ASCII value, so we're using the ASCII table. And you set the output pins to the character value, so we're sending that from the C program to the FPGA. And then we're going to read the input pins directly out of that, so the FPGA is going to run it through a circuit and then send back the output. We're going to read those pins that we're going to take that integer that it sends back to us, and we're going to turn that character into a character using the ASCII table, so we're going to map it, and we're going to add that character to the output string, and we're just going to keep doing that for everything. And then once we've done every letter in the original message, then we're going to display the new phrase to the user. It's pretty simple. This is kind of the high-level VLSI design. This is just a bunch of parallel adders put on together with XORs right here, so it can be adder subtractors. We have our 4 switches right here, and then we have our 8 input pins, which is going to be representing the ASCII value of the message. And so it's just run through a bunch of full adders, and we have our outputs down here. And so this is the structural modeling using Verilog. So here we have our structural, or we have a full adder module down here, which takes input A and B, and it has C in, and then outputs are sum and C out. Very similar. So this is just modeling one of these right here, and then it applies its logic to add or subtract, or to add there because it's a full adder. And then over here, my apologies, we're just putting multiple parallel adders in parallel using a wire to carry the outputs onto the next one, and then setting the sum along as we go. And then behavioral is a lot simpler. So we have a behavioral cipher where we have 8 inputs, and then we have 4 inputs. So these 8 are going to be from the GPIO pins, and these 4 are going to be from the switches. And then these 8 right here for the output reg is it's going to be going to the GPIO pins, so we can read it from our C program. And then input add sub is just defining whether you want to add or subtract. And then, oh, my apologies. I couldn't find my mouse. So basically what's happening, if add sub is equal to 1, then we're subtracting them. Otherwise, if it's equal to 0, then we're gonna add them together rather than subtract them. And then we just return that output to the GPIO pins, and then the C program can read that and turn it back into a character. So I'm gonna do a demonstration here. So I'm just gonna go over some of the issues. The biggest issue that I had was accessing the GPIO pins. Accessing from the C program was kind of tough because we ended up using bit structures that we hadn't particularly done in class, but it was really cool to learn them, set up the bit structures for there. And then the other problem was actually on the other way, the output has to be in a tri-state. It can't be just like a regular variable or anything like that, so it has to be able to be in a tri-state. That's why I had to add the enable switch onto there, because it has to have a chance to be turned off. Otherwise, it'll be an always on IO buffer, and you can't have that. And then the last part was moving from binary arrays. So when I originally started, I was turning everything from decimal into an array of zeros or ones, and I was trying to pass that to manually set each pin. And with the bit structures, I was able to completely pass that and make it so much simpler, where I'd be able to just pass everything as integers, and it'll automatically write it from the bit structures into the JP1 expansion port for the GPIO pins. I have a technical presentation here that'll go into a lot more depth. Feel free to look at that. I'm just going to go over a short demonstration here of what it actually looks like running on the board. So basically what we're going on here is we have the 10 switches right here, and we have the 2 hex displays, and then the actual where you enter the message is on the terminal running on the computer. So these first 4 pins is how you set the key, and then it's displayed here. This 5th pin right here is going to be that's for the enabled, that is for the encoding or decoding. So it's at low state now. So it's at a low state right now. So that means it's going to be encoding. If you flip it up, then it's going to be decoding. This last one here is the enable/disable. Right now it's in the off state. It has to be in the on state for the whole program to work. So always have this one on the end, because that allows it to be in a high impedance state, or chance to be. So that's the encoding or decoding. So we're going to set the key to 3. We're going to come up here. As you can see right here, it tells you the steps to do it. I've already gone over those. You set the enabling pin, you set the encoder decode, and then you set your key. So we're going to input a message. It's just let's do something simple, just hello. If you press enter, then you automatically get your output message back if it doesn't skip like that. We're right here. Yep, so we're automatically getting our output passage back. And so theoretically, if we go and change it from decoding to, or encoding to decoding, and we use the same exact key that we used before, which was 3, then we should get that same output message back. So all the outputs are turned into uppercase letters as well. Just for readability. Yep, so we get the hello back. Oh, my Mac's about to die. I don't want that to happen. So we're going to try a different one. So we're going to today's a good day. Then we're also going to go down and we're going to change the key. Let's say we want to change it to 6. And then right here, we forgot to set it back to encoding. So we're going to go back and set the encoding back to 0 so that we can encode it. And then we're going to input that. And then if we go ahead and set it to decoding with the same key, and we go ahead and copy and paste that back in, we should get our original message back out. And we did. Perfect. So that's pretty much it. Let's see. Yeah. That's just right here, sorry. I thank you. I really appreciate you coming out and listening to my presentation. I hope you have a good rest of your day.